Hi everyone, Mr. Boltri here, bringing you video 3.2, where we're going to talk about potential energy. Specifically, this is going to be kind of a longer video because we have to derive the equation for elastic potential energy and gravitational potential energy. And I could just tell you the equations right at the top, but remember, I sort of am of the philosophy that if you're going to use an equation, I really want you to understand where it came from. So we're going to do the whole derivation of each of these two equations in this video. So first, when we talk about elastic potential energy, we're most often talking about springs. But remember that this could be anything that is stretchy like a rubber band. As long as it follows Hooke's law, then it adheres to the rules for elastic potential energy. So as we discussed in class, the things that increase elastic potential energy are increasing the stretch, increasing the spring constant, and increasing the force. And this should all make sense because we can just go back to the idea that energy is the same as, or not the same as, but analogous to pain. The more pain something would cause, for example, if you took a spring and stretched it back farther, then that's going to also show more energy. So we have a natural intuitive sense of energy based on our senses for pain. So also to do this lab, we're going to have to recall Hooke's law, which relates the force of a spring and the stretch of a spring based on the linear graph that we did in the forces unit. And so remember that this negative sign just means that the force of a spring is a restorative force, meaning that if I pull it to the right, the force is going to be to the left and vice versa. But it's not really going to be super relevant for us since energy is a scalar. We're not really going to care about the signs of the force and the stretch. We're just going to care about the magnitude of the force and the stretch. Okay, so all that aside, now let's start to try to quantify elastic potential energy. And to do that, I'm going to present you with a scenario. So I have two springs. One of them is quite a bit stronger than the other, by which I mean it has a higher spring constant, higher K. The force versus stretch graph has a higher slope. So the blue spring you can see here is strong, and the weak spring you can see here is weak. And I can show you these springs in our next class. You will be able to feel one of them is significantly more stiff than the other one, even though they might look the same. So then if I attach these springs to, let's just say, a random cart, and you can see here the pink one goes with the red graph and the blue one goes with the blue graph. So this spring is stiffer, even though if it doesn't look like it. So then how can I use this setup to determine the elastic potential energy? Well, I can squish them both back and then let go and see what happens. And what happens is both of the cars sort of shoot up the ramp, which is at the same incline, identical inclines, identical carts, but different springs. So they both go up the incline, and then we can analyze the energy in the situation. So at the beginning, when I squish the spring back, that's storing a lot of elastic potential energy. Then that elastic potential energy gets converted into kinetic energy, which causes the cars to roll up the ramp. And then when it gets to the top of the ramp, it stops, and meaning that it has no spring and no elastic potential energy because the spring is unstretched, no kinetic energy because it's stopped. So it's just gravitational potential energy. So we can say all the spring energy converted to all of the gravitational potential energy. We know, just based on our conversation in class, that gravitational potential energy is influenced by mass and height. So if we can say that the gravitational potential energy for the pink car is the same as the gravitational potential energy for the blue car, then we can say that if these two are the same at the end, then that meant that the spring energy must have been the same at the beginning. And for us to be able to say that the gravitational potential energies are the same at the end, that would mean that their mass and their height would have to be the same. So because their masses are identical just to begin with, we have to find a certain amount that we need to push the springs back in order for their height to be at the end to be the same. And then we can say that the gravitational potential energy is the same at the end, therefore the elastic potential energy or spring potential energy was the same at the beginning. Okay, let's just try an example. We're just trying to figure out, we're just trying to get them to be the same height. So the first example that a lot of people think to try are, well, what would happen if we the two springs back the same distance. So let's squish them both by 5 centimeters and see what happens. Hopefully, it'd be really easy and cool if then the two carts went to the same height. So let's just see what happens with the two carts. And you'll notice that if I squish them back both 5 centimeters, the two carts do not go to the same height. The blue car goes quite a bit higher. So if we squish them both back the same amount, then they are not storing the same amount of energy. It's easier for us to say that they're not storing the same amount of energy because they go to different heights, meaning that they were storing different amounts of energy. So where do we go from here? Well, a lot of people think, okay, well, if doing the same stretch doesn't work, what if I squish them such that they have the same force? So I'm going to have to squish the red one quite a bit more than I'm going to have to squish the blue one, which I'm not going to have. So only 4 centimeters versus 8 centimeters. And let's see how that works. So that didn't do it either. We can see the red one goes quite a bit higher than the blue one. So if I squish them back such that both springs are exerting the same amount of force, then that also does not give us the same amount of energy. So then the question is, well, how do we get these two springs to be storing the same amount of energy? What can we set equal to each other on the graph? And hopefully, since you're all in calculus, you might already be thinking the answer is, well, what if we set the area of the graphs to be equal? So if I find the area of this region and then calculate how much I would have to stretch this one to have the same area, I see 5 centimeters and 7.1 centimeters. And those two are going to give me the same area. So if they go to the same height, then we can make certain claims on that. But let's not get too excited before we see if they do, in fact, go to the same height. So I'm going to squish one back 7 and one back 5, and we see that, when we squish them back such that the areas of the two graphs are the same, then they go to the same height, meaning that we can make the claim that the area of this force versus stretch graph is the elastic potential energy, or at least is reflective of the idea that the elastic potential energy for the two springs is the same. So that's really cool because first of all, it gives us a practical application of another integral, not just for displacement from a VT graph. We can find the area of a force versus stretch graph, and then that'll give us the elastic potential energy, which gets us back into calculus, which I know a lot of you have been missing. But it's also cool because now we can use that to write an equation for the elastic potential energy. 1/2 times the base times the height is the area of a triangle. So the elastic potential energy is 1/2 times the force times the stretch. And boom, right there, we have energy cornered because we are able to now quantify the elastic potential energy. Given a spring and a spring constant and a stretch, we can know how much energy is in that spring, which is a really cool thing. And just, you won't see this formula on your formula sheet because your formula sheet uses a tricky little substitution using Hooke's law and says that the elastic potential energy equals 1/2 times the spring constant times the stretch squared. But these two are the exact same formulas and come from the exact same place, the area of a force versus stretch graph. Which this is awesome because now that we have energy cornered, we can use our quantification of energy to, let's say, now derive the equation for the gravitational potential energy. So we can actually figure out exactly how much elastic potential energy there is at the beginning using this equation. And because we know that elastic potential energy converts into gravitational potential energy at the end, we can know how much gravitational potential energy there is also by just saying that all of the elastic potential energy turns into gravitational potential energy. So using that, we can squish it back a certain amount, figure out how much elastic potential energy there is, let it go, see how high it goes, and then know how much gravitational potential energy there is based on that height. So this is just so cool because we have energy cornered. Now that we have a equation for energy, we can just figure out all the equations based on just this one. So we have a graph that looks like this, is the gravitational potential energy, because we know that, and then how high it goes. And we can collect some data points and, good, this is linear, because linear stuff's really easy to analyze, and this video is getting a little bit long, so I kind of want to wrap it up. So don't forget to draw your line of best fit, and then we can write the equation for gravitational potential energy. So gravitational potential energy, y equals mx plus b, equals some slope times the change in height. and then plus 0. So that's good too. And so now the last thing that we have to do in this video is to figure out, well, what is the meaning of that slope? Well, first we should probably calculate the slope is 2.5 joules per meter. Okay, well, that doesn't really shout anything out to me, except for the fact that I haven't told you yet a very important piece of information, which is definitely worth writing down and putting a big star next to, is that a joule is actually a Newton times a meter. And this actually works out for the area of a stretch versus of an energy versus stretch graph, because that was just Newtons times meters. So a joule is a Newton times a meter. So our slope is actually 2.5 newtons times meters divided by meters. So it's actually really 2.5 newtons is the unit of our slope. So that should get us thinking, well, was there any situation in this lab where we were using 2.5 newtons? And I didn't tell you this, so you couldn't know, but the mass of my car was 0.26 kilograms, which means the force gravity on my car is 2.5 newtons. So therefore, I can say that the slope of this graph is the force of gravity, and we can do this experiment by and use different carts of different masses, and the slope is always going to end up to be the force of gravity. So the gravitational potential energy equals the force of gravity times the change in height. Actually, I should really probably put a change in gravitational potential energy equals the force of gravity times the change in height, because that just tells me how much the gravitational potential energy has changed in a given amount of time. And another way you could rewrite this, and I can't remember which one's on the formula sheet, I think it's the second one, is because we know force gravity is just mg times the change in height. So that was the derivation of two of the formulas for energy: gravitational potential energy and elastic potential energy. And what I'm really excited to do is I'm going to leave kinetic energy for you to figure out in our next class, either using one of the two equations that we just derived in this video. So the most important thing to remember from this video is the equations which are on your formula sheet. So you don't have to memorize those. I just wanted you to understand where those equations came from if you're going to be using it. So this is Mr. Boltri wrapping up a rather lengthy video 3.2 where we derive two equations for gravitational and elastic potential energy. Looking forward to doing more of these practice problems with you next class and deriving the equation for kinetic energy. But for now, go Bears.